The morning of April 8, 1943, over the coast of occupied France, Oberleutnant Egon Meyer pulled his Focke-Wulf 190 into a climbing turn at 18,000 feet. The Channel wind buffeted his canopy as he scanned the sky for the expected formation of American bombers returning from their raid on the Renault works outside Paris. What he saw instead made him momentarily question his vision. 7 enormous fighter aircraft, each one looking impossibly massive compared to anything he'd encountered, were descending in a loose formation toward his grup. They weren't the nimble Spitfires he'd grown accustomed to fighting. They weren't even the American P-38s with their distinctive twin booms that had recently appeared over Europe. These were something else entirely, something that looked less like a fighter and more like a flying bathtub with wings. Meyer, a veteran with over 60 confirmed kills, and the architect of the head-on attack method that had terrorized American bomber formations for months, felt a flicker of curiosity rather than concern. He'd read the intelligence briefings about a new American fighter called the Thunderbolt, but the reports had been dismissive. The aircraft was said to weigh nearly 8 tons fully loaded, more than twice the weight of his Focke-Wulf. Basic aerodynamics suggested it would be sluggish, easy prey for Germany's experienced fighter pilots. He armed his guns and dove toward the nearest P-47. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. What happened in the next 3 minutes would begin a fundamental reassessment within the Luftwaffe's fighter command. As Meyer closed to firing range, the American pilot didn't attempt to turn and dogfight as British pilots typically did. Instead, the massive fighter simply pointed its nose down and accelerated away in a dive that defied everything Meyer understood about aircraft performance. He followed, pushing his Focke-Wulf to its limits, the airframe beginning to shake as it approached 400 miles per hour. The American fighter pulled away as if Meyer were standing still. At 5,000 feet, unable to follow any farther without risking structural failure of his aircraft, Meyer pulled out of the dive and watched the Thunderbolt disappear into the haze over the Channel, easily exceeding 450 miles per hour in its descent. Back at his airfield, near Beaumont-le-Roger, Meyer filed a combat report that night that used the word unmöglich 3 times. Impossible. An 8-ton fighter that could outdive Germany's best interceptors. An aircraft that shrugged off damage that would have sent a Messerschmitt or Focke-Wulf spiraling to earth. Most troubling of all, an enemy that could choose when to fight and when to disengage with impunity. The report went up through channels to Luftwaffe High Command, where it was filed alongside dozens of similar accounts beginning to flow in from combat units across the Western Front. Something had changed in the air war. Something the German engineering establishment had insisted was aerodynamically impossible. The P-47 Thunderbolt represented a philosophical divergence in fighter design that would take the Luftwaffe nearly a year to fully comprehend. While German and British fighters had evolved toward lighter, more maneuverable designs optimized for turning dogfights, American engineers at Republic Aviation had built something fundamentally different. They had taken the most powerful aircraft engine in production, the Pratt Whitney R-2800 double Wasp, a massive 18-cylinder radial producing 2,300 horsepower in its early variants, and built the smallest possible airframe around it that could carry meaningful armament and fuel. The result was an aircraft that didn't try to outturn its opponents. It didn't need to. It could outclimb them, outdive them, and absorb punishment that would destroy lighter fighters. The R-2800 engine itself was a masterpiece of American industrial engineering that represented everything the German war economy was failing to achieve by 1943. Pratt & Whitney had begun development in 1937, building on lessons learned from their earlier radial engines. The double Wasp used 2 rows of 9 cylinders each, arranged in a radial configuration that provided exceptional power-to-weight ratio while maintaining reliability. Each cylinder displaced just over 100 cubic inches, giving the engine a total displacement of 2,800 cubic inches, hence its designation. But raw displacement only told part of the story. The engine's sophisticated 2-stage supercharger, designed to maintain power output at high altitudes, represented precision manufacturing at a scale Germany could no longer match. By the time the first P-47s reached England in late 1942, Pratt Whitney was producing over 1,000 R-2800 engines per month. The production line in East Hartford, Connecticut, operated with tolerances measured in thousandths of an inch, maintained by workers who had never built an aircraft engine before Pearl Harbor. Women who had been teachers and secretaries 18 months earlier were now assembling supercharger assemblies that performed flawlessly at 40,000 feet in temperatures 60 degrees below zero. The engine's reliability rate exceeded 95%. When one did fail, replacement engines were so abundant that aircraft were often back in service within hours. This industrial reality stood in stark contrast to what German fighter pilots were experiencing by mid-1943. The Daimler-Benz 601 engine that powered the Messerschmitt Bf 109, once the finest fighter engine in Europe, was becoming increasingly unreliable as quality control deteriorated under constant Allied bombing. Cylinder heads cracked, superchargers failed, oil consumption increased. Pilots learned to nurse their engines, avoiding full throttle except in combat, because replacement engines could take weeks to arrive. The BMW 801 radial in the Focke-Wulf 190 was more reliable, but it too suffered from material shortages that forced the use of substitute alloys that wore faster and required more frequent maintenance. The first systematic Luftwaffe evaluation of a captured P-47 occurred in late May 1943, when a Thunderbolt from the 56th Fighter Group made a forced landing near Saint-Omer after taking flak damage during an escort mission. The aircraft, largely intact, was transported to the Luftwaffe Test Center at Rechlin, where Germany's top test pilots and engineers could examine America's new fighter in detail. What they found during the teardown and subsequent flight tests challenged fundamental assumptions about fighter design that had guided German aviation for a decade. The engine alone weighed over 2,000 pounds without accessories, more than some entire German fighters had weighed in 1939. Yet, it was mounted in a way that placed the center of gravity perfectly for the aircraft's massive weight. The supercharger system used an intercooler that cooled compressed air before it entered the cylinders, extracting every possible horsepower from the fuel mixture. The Germans noted that this system was far more sophisticated than anything in production in Germany, requiring precision machining and exotic alloys that German industry was struggling to produce even for critical weapons systems. But it was during the flight tests that the captured Thunderbolt truly impressed and disturbed the Rechlin pilots. Oberstleutnant Hans-Werner Lersch, one of Germany's most experienced test pilots, took the aircraft up for evaluation in early June. His report, preserved in Luftwaffe records, described an aircraft that handled like a truck on the ground, but transformed into a different machine entirely above 10,000 feet. The massive engine, equipped with its turbo supercharger, actually gained power as altitude increased, maintaining over 2,000 horsepower at 25,000 feet, where German engines were gasping for air with barely half their sea-level output. Lerche performed a series of dives that would have torn the wings off most German fighters. The P-47 remained stable and controllable past 500 miles per hour, a speed at which Messerschmitts experienced severe control flutter and Focke-Wulfs risked structural failure. He climbed the aircraft to 40,000 feet, higher than any German production fighter except the latest Bf 109G variants could reach, and found the controls still responsive, the engine still producing power. Most remarkably, he fired the 850 caliber machine guns in short bursts, and found that the aircraft's mass absorbed the recoil with barely a tremor. German fighters, lighter and more delicate, often had their aim disrupted by their own weapon's recoil. The technical report that emerged from Rechlin in July 1943 made for sobering reading at Luftwaffe headquarters. The Americans had created a fighter that couldn't be caught if its pilot chose to disengage. They had done this not through aerodynamic sophistication or lightweight construction, but through brute force engineering backed by apparently limitless industrial capacity. The report estimated that building a single P-47 required approximately 3 times the machining hours of a Bf 109 and used specialized alloys that Germany was already rationing for submarine production and armor plate. Yet intelligence indicated that Republic Aviation was producing over 200 Thunderbolts per month and increasing, with production also beginning at a second plant in Evansville, Indiana. What the Rechlin report couldn't quantify, but what combat pilots were reporting with increasing frequency, was the psychological impact of facing an opponent who held all the tactical cards. Luftwaffe doctrine had been built around the assumption of technical parity or superiority. German fighters were supposed to outperform their opponents in key metrics, allowing German pilot skill and tactics to decide engagements. The Thunderbolt inverted this calculus. A mediocre American pilot in a P-47 could survive mistakes that would be fatal in any other fighter simply by diving away at full throttle. A skilled American pilot became nearly untouchable, able to choose the terms of every engagement. Major Heinz Baer, who would end the war with over 200 confirmed victories, encountered his first P-47s over the Ruhr Valley in August 1943. His account, recorded in a post-combat interview, captured the frustration that was becoming common among Luftwaffe pilots. They came down on us from above, made one firing pass, and then simply dove away before we could react. We gave chase, but it was hopeless. They pulled away from us as if we were training aircraft. When they had sufficient altitude again, they came back and repeated the process. We couldn't catch them, we couldn't escape them, and every attack they made cost us aircraft. The tactical revolution that Baer described was the result of American doctrine specifically designed to exploit the Thunderbolt's strengths. 8th Air Force fighter commanders had quickly realized that trying to dogfight German fighters was playing to the Luftwaffe's strengths. Instead, they developed what became known as dive and zoom tactics. P-47 formations would patrol at 25 to 30,000 feet, often 5,000 feet above the German interceptors climbing to attack bomber formations. When German fighters committed to their attack runs, diving through the bomber formations and then pulling up to attack again, they became vulnerable. The Thunderbolts would dive from above, building tremendous speed, make a single high-speed firing pass through the German formation, and then use their speed to zoom back up to altitude before the Germans could react. This wasn't the romantic, swirling dogfight that propaganda films had shown on both sides. It was systematic, almost mechanical killing that required discipline rather than individual heroism. American pilots were trained to resist the temptation to follow damaged German fighters down to lower altitudes where the lighter and more maneuverable Bf-109s and FW-190s could use their turning ability. Instead, they would make their pass and return to altitude, trusting that the cumulative effect of dozens of such attacks would wear down the Luftwaffe fighter force. The effect on German fighter pilot morale was measurable by late 1943. After-action reports began to include phrases like combat refused due to fuel situation or unable to pursue due to altitude disadvantage, with increasing frequency. These were often euphemisms for the hard reality that German pilots were avoiding combat with Thunderbolts unless they had significant numerical superiority and optimal positioning. The psychological transition from hunter to hunted was profoundly disorienting for pilots who had trained their entire careers for offensive combat. The technical specifications that made this possible were becoming clearer to German intelligence as more Thunderbolts were shot down and examined. The R-2800 engine in its water injection equipped variants could briefly produce over 2,600 horsepower for combat or emergency situations. This power was channeled through a massive four-bladed Hamilton standard propeller that was over 13 feet in diameter, larger than the entire fuselage of some early war fighters. The propeller alone weighed over 600 pounds, yet it was perfectly balanced and capable of maintaining efficiency across a wider speed range than any propeller system Germany had fielded. The airframe itself revealed American engineering priorities that differed fundamentally from German practice. Where German fighters used lightweight construction and minimum-gauge aluminum to save weight, the Thunderbolt structure was massively overbuilt by European standards. The main wing spar was a single forged piece of high-strength aluminum that could withstand loading forces that would buckle German wing structures. The fuselage used heavy-gauge skin that could absorb small-caliber hits without structural damage. The pilot sat in a cockpit protected by layers of armor plate that added hundreds of pounds, but turned the aircraft into a flying tank that could bring pilots home even after catastrophic damage. This durability was proving decisive in combat. Luftwaffe pilots were discovering that the standard tactic of attacking from behind and raking the target with machine gun and cannon fire was far less effective against Thunderbolts than against British or earlier American fighters. The thick skin and internal armor meant that pilots had to score direct hits on critical systems to bring down a P-47. Even then, the aircraft's robust construction often allowed it to continue flying long enough to reach friendly territory. German pilots began reporting shooting Thunderbolts that should have been fatal kills, only to watch them continue flying, trailing smoke but still under control. The intelligence reports flowing into Luftwaffe headquarters throughout the autumn of 1943 painted an increasingly troubling picture. American fighter production wasn't just matching German output, it was exceeding it by margins that seemed to defy rational analysis. In September alone, American factories delivered over 700 single-engine fighters to the 8th Air Force in England, while total German fighter production for all fronts that same month barely exceeded 1,000 aircraft. More concerning than the raw numbers was the sustainability of American production. Allied bombing was beginning to disrupt German supply chains and factory operations, while American industry operated beyond the reach of enemy action, working 3 shifts per day, 7 days per week. The captured documents and interrogations of American air crews revealed an industrial system that operated on principles alien to German wartime production. When an R-2800 engine failed, it wasn't repaired in the field, it was simply removed and replaced with a fresh engine from a depot stocked with hundreds of spares. The failed engine would be shipped back to the United States for rebuilding at centralized facilities equipped with specialized tools and trained technicians. This logistics chain meant that American fighter groups maintained readiness rates above 80%, while German fighter units were struggling to keep half their aircraft operational at any given time. The technical sophistication of the R-2800 became even more apparent as German engineers studied additional captured examples and interrogated American maintenance personnel taken prisoner. The engine's internal components revealed manufacturing tolerances that German industry could achieve only in laboratory conditions or for prototype production. The crankshaft, a massive forging that had to withstand thousands of explosive combustion events per minute, was machined to tolerances of 1/1000th of an inch across its entire length. The 18 connecting rods, each precisely balanced to identical weight, allowed the engine to run smoothly at over 2,700 revolutions per minute without the vibration that plagued German radial engines at high power settings. But perhaps most impressive was the engine's ignition system, which used 2 completely independent sets of spark plugs and magnetos. This redundancy meant that even if one complete ignition system failed due to combat damage or mechanical failure, the engine would continue running on the remaining system with only a slight loss of power. German engines used single ignition systems, making them vulnerable to a single point of failure. American engineers had built in redundancy at every critical juncture, accepting the additional weight and complexity in exchange for reliability that kept pilots alive and aircraft operational. The supercharger system represented another level of engineering sophistication that troubled German technical specialists. The 2-stage system used an auxiliary stage supercharger, driven by exhaust gases through a turbine, that pre-compressed air before it reached the main engine-driven supercharger. Between the 2 stages sat an intercooler that reduced the temperature of the compressed air, increasing its density and allowing more oxygen to pack into each cylinder. This entire system had to operate flawlessly in an environment where temperatures varied from over 300 degrees Fahrenheit in the turbocharger housing to 60 degrees below zero in the ambient air at altitude. The bearings alone in the turbocharger assembly required exotic alloys and precision manufacturing that consumed specialized machine tools and skilled labor. A single turbocharger contained over 40 individual parts, each machined to tolerances that left no room for error. Yet Pratt and Whitney and their subcontractors were producing these complex assemblies by the thousands, maintaining quality control that resulted in failure rates measured in fractions of a percent. When German engineers attempted to reverse engineer the turbocharger system for application to their own engines, they found that they lacked both the materials and the manufacturing capacity to produce it at scale. By early 1944, the tactical situation over Western Europe had evolved into a war of attrition that Germany was steadily losing. The appearance of long-range P-51 Mustangs that could escort bombers all the way to Berlin received more historical attention. But the Thunderbolts continued to extract a heavy toll, particularly in the medium-altitude battles over France and the Low Countries. Luftwaffe fighter units were being forced to operate under increasingly difficult conditions, with fuel shortages limiting training hours for new pilots and maintenance issues grounding larger percentages of the fighter force. The human cost of this technical and industrial disparity became brutally apparent in the Luftwaffe's casualty statistics. In January 1943, before the Thunderbolts arrived in significant numbers, the Luftwaffe fighter force had lost approximately 130 pilots killed or missing. By January 1944, with Thunderbolts and other American fighters operating in strength, monthly fighter pilot losses had climbed above 400. The mathematics of attrition were inexorable. Germany was producing approximately 2,000 new fighter pilots per year through its training system. They were losing them at nearly 5,000 per year in combat. The shortfall had to be made up by reducing training hours and sending less prepared pilots into combat, which only accelerated the loss rate. The experienced Luftwaffe pilots who survived into late 1944 began to adapt their tactics to the new reality. They learned to avoid engaging Thunderbolts unless they had overwhelming advantage in position and numbers. They focused their attacks on the bomber formations themselves, trying to inflict maximum damage during a single high-speed pass before American fighters could react. They became experts at reading the tactical situation from a distance, looking for isolated aircraft or formations that had become separated from their escorts. It was defensive, reactive combat, fundamentally different from the aggressive pursuit tactics that had dominated the early war years. Lieutenant Herbert Rollwage, flying with Jagdgeschwader 11, described the new tactical reality in his diary in March 1944. "We climb to altitude and watch the American formations approach. The bombers come first, their contrails visible from 50 kilometers away. Above them and behind them, the fighters, mostly Thunderbolts now, heavy and menacing. We position ourselves for the attack run, knowing we will have one chance, perhaps 30 seconds, before the fighters reach us. Then it becomes a race for survival. Dive away, stay at full throttle, pray the engine holds together long enough to reach the deck where we can use ground clutter to mask our escape." The physical toll of flying high-altitude combat in the increasingly desperate conditions of late war. Germany added to pilot stress. German fighters lacked the cockpit heating systems that American aircraft incorporated as standard equipment. At 30,000 feet, where temperatures dropped to 40 or 50 degrees below zero, German pilots flew in electrically heated suits that often malfunctioned or received insufficient power from generators that were increasingly unreliable. Frostbite casualties became common, with pilots returning from missions with blackened fingertips or toes from inadequate protection against the cold. The oxygen systems in German fighters were another source of problems that American pilots rarely experienced. German oxygen equipment used a demand system that required the pilot to actively inhale against resistance at high altitudes. Under the stress of combat, pilots sometimes forgot to breathe deeply enough, leading to gradual hypoxia that dulled reactions and impaired judgment. American oxygen systems used a positive pressure design that forced oxygen into the pilot's mask, maintaining blood oxygen levels automatically. It was a small technical difference that had large practical consequences in the split-second decisions of air combat. The ammunition capacity of the Thunderbolt represented yet another advantage that became apparent through sustained combat. The aircraft's 8 50 caliber machine guns were fed by ammunition boxes that held 425 rounds per gun for the inboard weapons and 500 rounds for the outboard guns, providing over 30 seconds of continuous fire. German fighters typically carried enough ammunition for 15 to 20 seconds of fire before running dry. In the chaos of high-speed combat, where deflection shooting required leading the target and multiple bursts to secure a kill, the ability to make multiple extended firing passes without concern for ammunition conservation was a decisive advantage. The 50 caliber Browning machine gun itself was proving to be an exceptionally effective weapon in the hands of American pilots. The armor-piercing incendiary rounds could penetrate the light armor of German fighters and set fuel tanks ablaze. The rate of fire, over 800 rounds per minute per gun, meant that a 1-second burst from all 8 guns put nearly 100 rounds into the air, creating a cone of destruction that didn't require pinpoint accuracy. German pilots learned to fear the distinctive sound of 50 caliber fire, a ripping snarl that meant a Thunderbolt was behind them with guns tracking. The psychological impact of the American fighter offensive extended beyond individual combat encounters. German fighter pilots knew, through intelligence briefings and their own observations, that they were fighting an enemy with apparently unlimited resources. Every Thunderbolt they shot down was replaced within days. Every pilot they killed was replaced by another fresh from training in the United States. Meanwhile, their own losses were irreplaceable. Experienced formation leaders and skilled veterans were dying at rates that left gaping holes in the tactical expertise of fighter units. The new pilots arriving as replacements often had less than 200 hours of total flight time compared to the 400 or more hours that had been standard in 1942. Major Günther Rahl, who would survive the war with over 270 confirmed victories, third highest among all Luftwaffe pilots, later recalled the transition from offensive to defensive operations with particular clarity. In 1940 and 41, we hunted. We chose when and where to fight, and we broke off combat when we chose. By 1944, we were the hunted. The Americans dictated the terms. They came over Germany in formations so large they blackened the sky, protected by fighters that we couldn't match technically and couldn't replace numerically. We fought because we had to, not because we wanted to. The Thunderbolt's ability to carry external stores transformed it from purely an air superiority fighter into a devastating ground attack platform, adding another dimension to the Luftwaffe's problems. By mid-1944, P-47s were regularly carrying bombs, rockets, or napalm tanks on underwing pylons, using their rugged construction and powerful engine to haul payloads that would have crippled lighter fighters. After escorting bombers to their targets and engaging any Luftwaffe fighters that appeared, Thunderbolt formations would descend to low altitude on their return journey and attack ground targets of opportunity. German ground forces and logistics networks quickly learned to fear these low-altitude sweeps. The Thunderbolt's 850 caliber guns were devastating against soft-skinned vehicles, trains, and troop concentrations. The aircraft's mass and structural strength allowed it to withstand the light flak that protected most tactical targets, while its speed made it difficult to hit with the heavier anti-aircraft guns that could bring it down. Luftwaffe airfields became particularly vulnerable, with parked aircraft, fuel trucks, and maintenance facilities all targeted by roving Thunderbolt formations. The attacks on Luftwaffe airfields created a vicious cycle that further degraded German fighter effectiveness. Aircraft that survived combat often couldn't be properly maintained because ground crews were forced to disperse equipment and work in hardened shelters to avoid strafing attacks. Fuel supplies had to be distributed and hidden, making refueling operations slower and more vulnerable to disruption. Pilots returning from missions often had to land at alternate airfields because their home base was under attack, separating them from their ground crews and familiar aircraft. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. The intelligence reaching Luftwaffe command through the first half of 1944 included increasingly alarming assessments of American industrial capacity. Interrogations of captured American aircrew revealed that the United States was producing over 8,000 combat aircraft per month across all types, with single-engine fighter production alone exceeding 3,000 per month. These numbers seemed so absurdly high that some German intelligence officers initially dismissed them as disinformation. Follow-up analysis using production facility assessments, shipping data, and observed aircraft delivery rates confirmed the figures were, if anything, conservative. The American ability to produce the R-2800 engine at scale particularly impressed German technical intelligence. By mid-1944, Pratt Whitney and licensed manufacturers were producing over 4,000 R-2800 engines per month, not just for P-47s, but also for other aircraft types, including the F-6F Hellcat naval fighter, the A-26 Invader attack bomber, and the C-46 Commando transport. This single engine type, in its various versions, was being produced at rates that exceeded total German aircraft engine production across all types. The production system that enabled this output operated on principles that seemed almost incomprehensible to German observers accustomed to craft-based manufacturing traditions. American factories used assembly line techniques pioneered in automobile production, with the complex task of building an aircraft engine broken down into hundreds of individual operations, performed by semi-skilled workers, using specialized tools and fixtures. Each worker became an expert in a narrow range of tasks, achieving both speed and quality through repetition and standardization. The quality control systems employed in American factories ensured consistency across thousands of engines. Critical components like crankshafts and cylinder barrels were subject to multiple inspections using precision measuring equipment. Test cells ran sample engines through punishing cycles that simulated combat conditions before the engines were approved for installation in aircraft. The entire production system was designed to eliminate variation and ensure that an engine produced in January would perform identically to one produced in June, regardless of which specific workers had built either unit. German production, by contrast, still relied heavily on skilled craftsmen who hand-fitted components and used individual judgment to achieve final tolerances. This approach produced excellent engines when materials and time were abundant, but it couldn't scale to meet wartime demand, and it made quality highly dependent on the skill level of individual workers. As Germany mobilized forced labor and concentration camp prisoners to supplement its depleted workforce, quality control became increasingly difficult to maintain. Engines reached frontline units with defects that wouldn't have passed inspection 2 years earlier. The contrast between American abundance and German scarcity manifested in countless small ways that collectively created overwhelming American advantage. American fighters had electrical systems powerful enough to operate radios, gun heaters, navigation aids, and cockpit instruments simultaneously. German fighters increasingly suffered from electrical systems that were marginally adequate at best, with pilots having to choose which systems to power during critical phases of flight. American pilots wore standardized, well-fitting flight equipment that kept them warm and protected. German pilots wore whatever their unit supply officer could scrounge, often mixing obsolete or captured items with standard-issue gear. The fuel situation became perhaps the most critical limiting factor on Luftwaffe operations during the last year of the war. Allied bombing systematically targeted synthetic fuel plants and refineries throughout Germany and occupied territory. German fighter units that had operated on allocations of thousands of gallons of aviation fuel per day in 1943 were reduced to hundreds of gallons per day by mid-1944. Training flights were cancelled. Operational sorties were limited to only the most critical missions. Pilots sat on the ground watching American formations pass overhead because there simply wasn't fuel to allow them to take off and engage. The synthetic fuel plants that Germany depended on for aviation gasoline were marvels of chemical engineering, using the Fischer-Tropsch process to create liquid fuels from coal. But they were also large, fixed installations that couldn't be hidden or quickly relocated. American heavy bombers, escorted by seemingly endless formations of fighters, including Thunderbolts, struck these facilities repeatedly throughout 1944. Repair crews would restore production within weeks, only to see the plants bombed again. By autumn 1944, German aviation fuel production had collapsed to less than 30% of the previous year's output. The quality of German aviation fuel also deteriorated as refiners struggled with feedstock shortages and damaged equipment. Octane ratings dropped, reducing engine performance and increasing the risk of detonation that could destroy engines. Pilots learned to treat their aircraft more gently, avoiding full throttle settings that might have been routine a year earlier. The psychological effect of flying an underpowered aircraft into combat against opponents who could use full power without concern was demoralizing beyond what statistics could capture. By the autumn of 1944, the Luftwaffe fighter force was a shadow of what it had been even 6 months earlier. Operation Bodenplatte, the massive New Year's Day 1945 strike against Allied airfields, would temporarily demonstrate that Germany could still mass hundreds of fighters for a coordinated operation, but the losses suffered in that attack effectively destroyed the Luftwaffe as an organized fighting force. The Thunderbolts and other American fighters had achieved air superiority not through any single decisive battle, but through relentless attrition that Germany's shrinking industrial base and collapsing logistics network couldn't sustain. The pilots who flew those last desperate missions understood the futility of their situation. They fought because they were ordered to fight, because they hoped to protect German cities from the bombers, or simply because fighting was all they knew. But they weren't fighting to win anymore. They were fighting to survive long enough to see the war's end, knowing that every sortie might be their last, knowing that the massive American fighters that had once seemed so ungainly and vulnerable had proven to be the instruments of their defeat. The technical specifications that had made this outcome inevitable were evident from the beginning, though few understood their implications at the time. An 8-ton fighter, powered by a 2,600 horsepower engine, capable of diving at 500 miles per hour and climbing to 40,000 feet, represented industrial and engineering capacity that Germany couldn't match in 1943 and certainly couldn't match in 1945. The R-2800 engine, produced by the thousands in factories that operated beyond the reach of German attack, symbolized American industrial power in its most concentrated form. The Luftwaffe pilots who first encountered Thunderbolts in the spring of 1943 had expected to face another variant on familiar themes, a fighter that they could outmaneuver, outclimb, or outrun using tactics refined through years of combat. What they encountered instead was something fundamentally different, a fighter designed not to beat German aircraft at their own game, but to render that game irrelevant. The Thunderbolt didn't need to turn inside a Bf-109 or match the roll rate of an FFW-190. It simply needed to be faster in the dive, more durable under fire, and available in numbers that made every tactical victory by German pilots into a strategic defeat. The story of the R-2800 engine and the fighter it powered is ultimately a story about industrial warfare and the mathematics of attrition. Germany entered the Second World War with qualitative advantages in many categories of military equipment, including aircraft. But wars of attrition aren't decided by who has the best equipment. They're decided by who can produce, maintain, and replace equipment at a rate that the enemy cannot match. The United States, with its continental-scale industrial base operating beyond the range of enemy attack, could absorb losses that would have been crippling to any European nation and respond by increasing production. The psychological journey of Luftwaffe pilots from confidence to resignation mirrored Germany's trajectory through the war. In 1940, Germany's fighter pilots believed they were technically superior and tactically invincible. By 1943, they were beginning to understand that technical parity was slipping away. By 1944, they knew they were fighting an enemy they couldn't defeat, trying to delay an outcome that was already determined. The Thunderbolt, massive and seemingly crude in its design philosophy, came to symbolize that harsh reality more effectively than any propaganda could have communicated. In the final accounting, the P-47 Thunderbolt destroyed more German aircraft than any other American fighter type, with over 3,800 confirmed air-to-air victories. It flew more than 500,000 combat sorties, dropped over 130,000 tons of bombs, and fired over 135 million rounds of 50 caliber ammunition. More importantly, it achieved what strategic weapons are designed to achieve. It fundamentally altered the enemy's calculations about what was possible, forcing them into tactical and strategic postures that accelerated their defeat. The German engineers and pilots who examined captured Thunderbolts, who faced them in combat, or who simply watched them pass overhead in ever-increasing numbers, were witnessing their own technological and industrial obsolescence. The R-2800 engine, running smoothly at power settings that would have destroyed German engines, symbolized an industrial system that had mastered mass production without sacrificing quality, that had solved problems through engineering rather than accepting limitations, and that could sustain operations at a tempo that exhausted its opponents. Thank you for watching. For more detailed historical breakdowns, check out the other videos on your screen now, and don't forget to subscribe.